very quickly, now it's week 6. So we will have midterms in week 8. So now we are just 2 weeks ahead. Okay, but anyway, for midterm we may have just some simple questions. It's not difficult, and you may need to start to prepare your final project. Okay. So today we are going to explain the radio access technology. Last week we have been talking about the 5G frequency spectrum because we are going to transmit. We want to have a faster network. We need to have a wider bandwidth to accommodate more users, more devices, especially IoT devices. Okay, so today we are trying to explain the technology or enablers which used to make the data go through the network, I mean the radio, and get down to our internet, like this. Okay. But for myself, my background is not telecommunication. Okay, but maybe we have some students from electronics department. Maybe you are better than me, so I say something not correct, you may just correct me. But like I say, this courses is aimed on the students who are not electronics background. And we only focus on the intelligent manufacturing field application. Okay, so I would like to introduce some tools which may be useful for you. Okay, so to develop something I don't even never used before. Okay, but of course we will still have some. We will still learn something which is useful, like 5G core. Okay, which will be very helpful for you to learn how to construct a network. Okay, later in our last hour, Manel will have some briefing introduction to help you to know how to use the network with 5G core, the open source platform. But the literature is also very important because once you are going to input some parameters, you need to have the knowledge, right, to put the parameters, right. Okay, so it's quite important to know some basic knowledge. Okay, so today we have 2 portions. First, I would like to talk about essence. And then remember on the week 2, when we talk about chapter 1, we talk about radios, right? How does the radio can carry data, right? So we talk about the amplitude modulation, the frequency modulation, and also phase. I mean the time differences, phase, right? Modulation, and both we combine them. They call it QAM, and we will talk about this when we are going to talk about the orthogonal frequency division multiplexing. I think we have been mentioned this earlier, but not very clear. We will give more information for this to tell you how to carry the data through this. Because we are going to carry tremendous data. We talk about gigabytes. Okay, not a K bit or K omega bits. Okay, because that's too slow. So for 5G, usually we will divide it to 3 categories. One is sub-G, remember? And the other one is 3 gigahertz, 3 giga to 6 giga. For three giga and 6 giga. For 6 giga we use TDD, and for 3 giga we use FDD, and then we may use 27.8 gigahertz to 6 gigahertz to 30 gigahertz is we call a centimeter wave. And for the frequency higher than 30 gigahertz, we call this is mini wave, a millimeter wave. Okay, so that's what we are going to introduce in the radio access. Then we will talk about the pre-standard, where is the standard comes from before it becomes standard. Basically, today's 5G is based on the technology developed by the Korean Telecom, their special industry group. Okay. So all of the 5G standards is based on from here, and we will introduce transmitter and a receiver setup. Unfortunately, in our class we don't have our hardware. Okay, sorry about this, but we will just tell you if you need to set up the hardware, there is a reference. Okay, but once we set up the hardware, what test should you do? Usually we will conduct something we call MIMOs. Okay, that means there is a transmitter and here is a receiver. So we may have many antennas. Right? Like this one, we may call this 4 by 4. I mean there is 4 antennas. And there is 4 antenna for a receiver. But we can have a different kind of configuration to enhance the data transmission efficiency. For example, we have 4 antenna, right? So we can have the antenna transmit same data. For example, 0, 0, 1, 0, 0, 0, 1, 0. So everyone transmit the same data. So if anything missed, you still can catch one. Just think of if the receiver is very far away and the signal is very weak, right? So we are sending the same thing. So even one is missed. This one missed, this one missed, this one missed, but this one catch. So you got the data. So we enhance. But it's too slow, right? How about, but if it's close, how about we sending different data? For example, I said 0, 0, 1, 0, and the other one said 0, 0, 1, 1, and then 0, 1, 0, 1, right? Or 1, 1, 1, 1, something like this. In the first manner, I am sending the same thing, so I have to send this first. Then I send the other one, and I send the other one. I send the other one. Right? It will take a long time. But now we are close. So we can setting these four information at the same time. So it's close. So the signal is very strong. Also the strength is good. Signal is good. So the speed is more faster. Right? Okay, so that's a multi input and multi output. We will watch a video and then you will understand more. Okay. So you can enhance or you can transmit the data clearly. But how about we have a larger antenna array? Maybe 8 by 8. I mean, we have a double antenna. But of course, we have more antennas. You can transmit the data more faster. But the question is, it will be more costly, more expensive. So it depends on the capacity you require, right? So you cannot say, oh, we want to pick a dinner, like the Wi-Fi. You know, in our classroom, we are not going to buy a very expensive Wi-Fi app because we don't have many users, right? We may have 20 students maximum, 20 or 30 students. Okay, but if we are in a big conference room, we may try to have big antennas, which can run more efficiently with better quality of user experience. And we also will talk about download physical data. Okay, that's a data frame. You know data frame? You know data frame ideas. I give you ideas. I think you all know the OSI layer, right? That's an open system interconnected network, right? So from bottom, it's a perception layer. It's called I/O. The data from 01, 01, something like this. And then we have data link there. And then we have network and the transport layer. That's TCP, IP. I think you are familiar with this. Data link is a frame. Well, what's frame? Frame may contain something like ID and like a function and the payload. That's data and check, secure check. So that's a frame. So it's a byte. So you may have many elements to become kind of a command. Right? Okay, so that's That's the best concept. So here, it was explained how can we put the data into the DM or OFDM to transmit data. Okay. So here says like for download the content, it may require 4 OFDM symbols. And later we will explain what is the symbol. For chapter 3, it includes six subsections. Okay, but today we will only go through the 3.1 to 3.3. Okay, so in this week we were talking about basic building blocks. Okay, this is can help us to understand the basic architectures and the minor, massive multi-input and output, and the downlink physical layer. And the system information forecast. Your cell phone is always connected to the network system, right? But usually your devices were trying to keep minimized connection with a radio station, just to try to keep alive. You know what I mean? Your cell phone is always linked with the 5G new radio station. Well, but probably maybe 1 or 2 minutes you will try to contact, send messages, means I'm connected to the network. That's it. Okay, so they have some system information forecast methods. And the download data transmission. That's all we are going to go through. Okay, but next week we will talk about upper link physical layer. Upper link and the downlink, they both based on the OFDM, orthogonal frequency division multiplexing. But they have a little bit different. Like for download, they call a cycling prefix. That's a method to eliminate or reduce mistake. So basically, how do they reduce the mistake? For example, they are sending the data like x1, x2, x3, right? X neo, like this, right? But like I say, this can be a frame, right? A frame. So let me this message finish. So for cyclic prefix CF, they try to double this. This is another message, right? This is the first one, this is the next one. But they double this. So we will be able to know this is the end. Okay, in case it's mixed. We know the 5G, the radio transmission is very fast. So it's very easy to lose some data. So they do have some methods to prevent the data loss. Like I just said, they can sending us same data, right? So in case, the weak signal, so they may not be able to receive it. Okay, but this week we are not going to talk about some physical information like MAC, the medium access control MAC, and radio link control, and something like a pocket data conversion protocols, PDCP, and the service data adoption protocol, SDAP, and the radio resource control, RRC. But where we see this, remember? I think before we have been talking about this. Remember, CA, carrier aggregation, and dual connectivity. Because we want to boost the data transmission speed, right? So we need to like this one. This one, the devices, the user equipment connect to the same one base station. But how can we boost the data throughput? So we may have two physical connection here. Okay, so the data is split in the MAC. You see that? That's MAC. But for dual connectivity, the method is different. The method, they split the data in the PDCP, but not MAC. Why? Because these are two different radio stations, right? So they have to split the data. So the blue one, this one is master cell group. Okay. The yellow line is split, master cell group. Okay, anyway, we know this is split in the PDCP, but this one is split in the MAC. Understand? But which one is faster? I don't know. But sometimes this can be faster. The 1, 2, 3, 4, and this can only deliver one, and the 2, 3, 4 is still on the way. Okay. But maybe I think it depends on the signal strength, how close the devices to the radio station. If it's more far away, I mean the UE is more far away, we know the signal will be weak. The transmission speed will be slow. Okay, but the signal is weak. How can we enhance? We can use beamforming to enhance. I mean, same antenna to push the same data. Okay, so the radio signal can be stronger. Understand? Anyway, the rule is just like what I said. We can sending same data, or we are sending different data. That's all. It depends on your configuration, and then you will decide by the signal. I mean, the user devices and equipment, UE, or we call you user equipments, to the radio station. Okay, we are not going to talk about this, but we will only go through this. Mac, PDCP will be explained next week. Okay, so what's MAC? MAC is medium access control, radio link control, and PDCP, pocket. Pocket data is this. 4 symbols. But why is it simple? Well, before we talk about maybe we I think I showed this before, right? So that's a symbol. Symbol 0, symbol 1, symbol 2, symbol 3. This will consist this. That's a data frame, the download physical layer. So this will be a set data. Now why this? Remember, the data is like the IO, right? So we may say 8-bit or 60-bit, right? So there's why is it 50? It's not correct. It should be 60. I think it's 60. Yeah, it's 60. So why is it 50? Okay, anyway, we know this is frequency, right? So if we will check this, if this peak, we will recognize this maybe 1. This maybe 0, something like this. Okay, and by the time, that's time, right? So by the time we were sending this, so like I say, the data is like a frame, right? So we know this is a 60-bit. I don't know why here is a 50. 50. Maybe I'm wrong. 2, 4, 6, 8, right? 10, 12, 14. Well, but anyway, you understand, right? So you become like a matrix. So you continue setting the data. Okay, so it's more efficient if we compare with we mentioned earlier in chapter in chapter 2, no, in week 2. Remember this, right? That's a AM, FM, and time domain, frequency domain, and we use this as a quantum, quantitude, amplitude modulation cause both amplitude and phase of the carrier to change. Okay, the advantage of quantum is the capability of representing a large group of bits as a single amplitude and phase combination. Okay, anyway, this is basic. So once you know the idea, it's much easier to understand what it is. Okay. So maybe we watch a video so you can be easier to understand how to transform.
What is orthogonal frequency division multiplexing and why is it used? And if you're interested in these topics, please subscribe to the channel by hitting the subscribe button and check out my webpage. That's in the description below. You'll find over 250 videos in categorized order. Let's start by considering sending digital data. And here's a sequence of digital data. Now, to send this, we need waveforms that are in the time domain. And so, for example, for sending the first 0, we might choose this waveform here, where we make the voltage go from up to a level of 1 volt for a period of time, capital T. Then to send the next bit of digital data, we might have a waveform that starts at time T and sends a negative 1 volt, because this is a different bit of digital data. So if we represent our zeros as 1 volt and our ones as negative 1, then to send the next bit of data, we would have this waveform here, where we're going to start it, it's going to transmit in the third time slot with a positive 1, and so on for all the other data that we are wanting to send. Now, when we're sending these, we send all these waveforms, we're going to add them all up, and then if it's a wireless channel, we need to multiply it by a carrier to get it up to a frequency that causes the antenna to oscillate. So this is standard modulation. This is not OFDM yet, but we want to think about this so that we can understand OFDM. So what does the waveform look like in this standard communications case? Well, I've drawn it out here, where I've drawn it for a carrier which has 2 oscillations per time slot, capital T. In practice, it would be much higher than that, but I'm just drawing it here to show what's going on. So here you can see over the time period from 0 to T, you've got a cos wave. That's because that's positive 1 times the cos wave carrier. In the next time slot, it's the negative cos wave because we've got it multiplying by a minus 1 volt because that was a digital 1, and so on. And you can see this waveform, a couple of characteristics. It's got a constant amplitude level of the cos wave, but there are these sharp transitions that happen at the time slots between digital transitions of data. So where it went from a 0 to a 1 or a 1 to a 0, you're going to get these sharp transitions. This is typical of standard direct modulation. So what is OFDM? And I've drawn this one like this so that we can understand OFDM in relation to this. So
okay, so you may watch this after you go home. But anyway, this is the basic concept to carry the I/O, I mean digital signal. I think you guys should know, right? But probably are you studying telecommunication? No? You do? Okay, probably you notice you can watch this at home. This video will take about 50 minutes. Okay, but I just try to say, that you know the concept. Okay. So that's a basic bandwidth, and let's look at this. That's bandwidth for typical internet connection, and that's a digital bandwidth definition. Okay, so that's a classical bandwidth definition. That's bandwidth, and we just explain what is a carrier. Okay. Okay, but however, for today, you are connect the internet with Wi-Fi 6. The maximum speed can reach 9.6 gigabits. It's pretty fast, but we know the difference. Wi-Fi has different algorithm to the 5G, right? But this one doesn't have a 5G call. It cannot manage the network, right? Okay, so if we are going to construct intelligent manufacturing field, I think it still need to implement 5G core, because 5G core will cover any kind of radio assets, right? Okay. And for understanding the new radio bandwidth paths, and we just explained what is carrier, right? Okay, so the carrier inside may have the parts we call the bandwidth parts, BWP. So it may include many BWP, bandwidth parts. Okay, but you need to separate them. You need to have a subdivide to avoid interference. Right? But the span is a very how can I say, precious, because the bandwidth is limited. Right? We don't want to waste. We don't want to waste the bandwidth in something not useful, seems not useful. But it's important to keep the interference away in the transmission. Okay, I think we just need to have some basic concept. But in actual radio waves, it's a stereo. I mean, it's a 3D direction. It's not one direction. Then you will do like this. So the radio pattern will be like this. So once you are going to run simulation, if you are doing research with telecommunication, they may ask you to key in some information like this. Before, I have invited some expert to give a talk about this, but unfortunately, this year we don't have expert to explain this. So, but I just let you know, if you are going to do some simulation, you need to have a radio patterns which can represent the gain of your radio, right? The gain is quite important in your simulation. Okay, anyway, if you are doing some researches, especially we have a student from Professor Wang's lab, you can read this to study. Okay, there is a toolbox which provides standard compliance functions and a reference example for modeling, simulation, and verification of 5G new radio. Last year, Mandel have demonstrated this and helped students to construct some model exercise. But this year we changed this. Okay, because we changed to 5G. 5G call, because we think maybe this can be more common use. Maybe it can benefit to more students. Okay. Because not everyone are experts on electronics or telecommunication. Okay, anyway, you need to have a wave generation, right? Generate wave, and the sub carrier and number knowledge. But usually, the toolbox they will provide you all information, knowledge you need to have. Okay, but it's good to have the literature before you do this. Okay, so like this one, there's a physical download share channel, PDSCH, and a physical uplink share channel throughput. That's what we want to know, right? Because you want to know how fast your network can deliver data. That's everything we want. That's what we focus on. That's the purpose for taking this class. We need to know how can we construct a proper network which can meet the quality of user experience. So here we'll tell you the signal reception, right? And the text and the management, link measurement. Okay, that's major for the 5G neural radio models. Okay, there's more modules, but we are not going to give more information. You may study by yourself. Okay, so this class I may just introduce the information for you. Okay, so let's look at the chapter 3. It starts with evolution toward 5G pre-standard solution. Okay, in the beginning, in the beginning we start with 3G, 2G, right? At that time, the data transmission rate is quite slow. Maximum can be download speed can be 3 megabit per second, and the uplink is about just 768 kbit per second. That's pretty slow. Then after they released the technology called HSUPA from 1.4 megabit per second to 5.7 per second in release 6. Anyway, after we introduce the new technologies, like cyclic prefix, orthogonal, the frequency division, multi-access, then the speed increased to the hundreds, 100 to 150 megabit per second. So it's much faster. Okay. Anyway, this information is. But I have questions. Why download is always faster than upload? Download. Can we make upload faster? Can we make download fast? No, download is fast. Upload is much slower. And as I say, they use a different modulation method. Like the download, we use a cyclic prefix. Do you know why? Or there's no reason, just because the configuration like this. Or we can make upload faster. Yeah, I think we can. We can make it faster. Because of 5G, 5G core, you can customize. You can define your bandwidth. But before, you cannot. Okay, anyway, here talk about architectures. That's a user panel. Remember, before, in 4G, user panel, control panel, they are not separate. They are together. right? So start from 5G. We separate them. Okay, so that's the model or architecture, platform architecture, protocol architecture. When we start, right? Radio link control, MAC, and what is partition, sorry, I forget, PDCP, right? So that's they proposed. But before, LT, that's LT physical layer, is like this. So this will be used to control the LTE network. Okay, so in 5G, we also proposed the customer premises equipment, CPE devices, at home. So in the future, we don't need to set up the fiber to the individual home. You just need to have a CPE, customer premises equipment, that you can link to the new radios. Okay, here has some operation spec. Okay, so operation a 28 gigahertz is pretty high. It's much higher than our cell phone, right? Our cell phone is running sub 6G. Okay, and here is a conventional CP OFDMA. What is CP OFDMA? That's a cyclic prefix. I have I will make a note here, not here. That's week. This week, every week I will make a class note, so you can check the summary. What I say, like today's, I summarize it like here. So here explained what is cyclic prefix. And there's a videos to explain this. Okay, so if you check I think I put here. Okay, that's is what cyclic prefix. So you watch a video, you will explain this. So the process of prefixing the last bit of frame at the beginning to avoid, inter-symbol interference. So you see this originally is X3, right? So it will have a prefix X3 here. That's a window 1, window 2. Okay, so that's OFDM. For uplink, you see the method is a discrete Fourier transform, spread, orthogonals, division, multiplexing. Okay, remember I say why upload? Download is faster than upload. Of course, you can control, you can assign the network, but you may not change this because the modulation methods are different. I mean, for the upload, it may take more resources or bandwidth. So they are different. One is CP, right? One is discrete, Fourier transformation, separate, or so forth. Okay. So here you can see more clear. Okay. So there is a subcarrier peak, and that's这叫什么 ？Sinoid function side lobes. Okay, and that's a subcarrier nodes. Okay, but how does it transmit the data? So we will start a frequency domain claim, right? So that's a mapping claim source data onto an orthogonal subcarrier. So we will have this convert to this. Okay, so this is 1, 2, 3, 4, 4. So 8. So this is 16 antenna. And you will transmit through from the time domain some of sinusoid and receiver and the frequency domain. And at the end, recover map to QAM source data. So the data transmission will be like this. That's the data we convert to the frequency and transmit. It's on time domain. And receive. And the frequency domain quiet. Then we got the data. Okay, so here explain the process. And here is the physical information. Like here, there are 52 subcarrier, and there are 48 data for pilot, and 1 subcarrier, and 312.5 kHz carrier separation, and the bandwidth is about 20 megahertz. Okay, so data will be like this, and transform to the FFT blocks. So like this, encode interleaf groups and map onto the constellation, and load 52 complex value into FFT. So you will load into the blocks and convert subcarrier to time domain. Okay, time domain. Okay, so once you send in the data, you will base on time domain, right? Okay, add guard interval. This interval, guard interval. See this? This is guard interval. There is more detail you can read this website. If I do not explain clear, you can read this by yourself. Okay, but at least we know the meaning, right? Symbol and interval. That's a process, you see, and the transmit as one symbol. Repeat process for new symbol. So you finish one little, right? 1, 2, 3, one by one. That's how we conduct the radio access. Okay, this part is more technical. But anyway, here, if you are running some hardware or you conduct some simulation, and you might need to know that's the strength, right? The signal strength, dB, the strength. Okay, I think I explained this. Okay, so here is some reference I found on internet. Okay, so this example has been done last year. Okay, I think it's a good reference. So this article explained how OFDM, orthogonal frequency division multiplexing symbols and the carrier work. It covers modulation, mapping. Okay, so you may follow the step to carry out the exercise as modulation, mapping, symbol, and carrier. Okay, so that's a symbol S0, S1, 2, 3, 4, 5, 6, 7. Symbol 2, 8, 9, something like this. So after you finished, you put the subcarrier frequency, then time domain conversion. Okay, so that's a transmitter side. That's the data, input data you are going to transmit. Okay, like this one. 1 0 1 0 1 1 0 0 1 0, something like this. Okay, so it will convert to something like this. Okay, and that's a 16 quant. This is not in the textbook, but anyway, inversely, you will receive the binary data. So if we look at the process here, that will be pretty clear, right? So understand? If you are going to carry out the exercise, this is a basic process. And here is examples, the reference. Okay, that's a transmit. That's the receiver side. It's 2:30. Well, maybe we should take a break. Let me check what else. Okay, maybe now it's 2:30, so let's take a 10 minutes break, and we will come back at 2:30, 2:40.